Hey class, welcome. I want to start by congratulating those teams that did a really good job on their study team test. And if you were actively involved in that and you understand what you were doing together collectively, I think you should do pretty well on your individual test tomorrow. For those of you that weren't exactly excited with your individual score, um, again, tomorrow is a chance for you to do better. And I hope that you find this helpful in kind of explaining some of the concepts that you may have missed. So let's start with number one. It says examine the graph at right. And the question is, does this relationship appear to be a function? And the big criteria we have for a function is that in order for a relationship to be a function, if I pick a value, like 5, and I give it to the function, it gives me back, see, I'm coming up here, this function reaches the number 7. So when I give the function 5, it gives me 7. And you can see it only gives me 7. So it consistently and predictably says 7 every single time I give it 5. In other words, there's not another value other than 7 for 5. If I give it the number 1, you can see every single time it gives me the answer of 4. So 1 says 4, 1 says 4. 1 never says anything other than 4. So in order for a relationship to be a function, each x value can only give me at most one y value. Let's look at a couple of relationships that I've put together here. This first one is this relationship, and the question is it a function? Well, as I move across the domain and I pick a domain value, like I'll pick 0, right? When I pick 0, this function says -2. And every single time I give it 0, it says -2. If I give this function the number, I don't know, 9, 9 is apparently giving me a value of 4. And every single time I give this function 9, it gives me 4. So this appears to be a function. Let's look at, not this one, let's look at this one. Okay, so to contrast that, look, if you look closely at this, when I give this function the number 9, you can see sometimes it gives me +3, but it is also possible for it to give me -3. So because this value of x produces both a +3 and a -3, we have to say that this relationship is not a function because this x value has more than one possible y value. That's the key thing. If I look at this relationship, right, this black curve, as I move along the domain again, you can see every single time I stop, this x value of 1 gives me a y value of about 2 1/3 maybe, right? When I give it an x value of 0, it's giving me about 3. So it appears that this is a function because each x is 2, it only says 4, right? It doesn't give me more than one value for y. And then this is another example of a relationship that is not a function. And the reason why, again, is if I pick an x, you can see that there's two different y's that are possible. So a relationship that is a function, right, can only have one possible y value. So this, we're going to just say, yeah, this is a function, then we'll say why. So you can see on here I've written, yes, this is a function because each x value gets at most one y value. The next question we have is, what's the domain of this function? And I always do this, right? When I'm talking about the domain, it's the x values. It's those input values along the x-axis, right, that are possible. Now, if I look at this particular function, I can see there's a lot of values that I don't get x's for. In fact, I'll highlight these in red. None of these values, if I put them into the function, none of them are going to give me an output, right? Because those inputs don't produce an output, they're not in the domain of this function. And over here, these values are not part of the domain of this function. It looks like the very smallest value that's part of the domain is the number -3. And if I go all the way from -3 all the way up to +6, all of those numbers along there are members of the domain. Those are all of the x values that will produce y values. When I give it an x, it'll give me back a y. So I would say my domain for this function is all the values from -3 to +6. And it's perfectly acceptable to just write that out in words. I'm saying here the domain is the x values from 3 to 6, right? The x values from 3 to 6 are possible inputs. They're part of the domain. The other way we can say it is this shortcut notation. We can write it like this. So I can also say that the smallest is -3. We're talking about the x's, and the biggest it can get is to 6. So the domain is all the x's between -3 and +6. And then in terms of what outputs are possible, because that's what the range is, the range asks us what are the outputs that are possible. So if I look at this function, I can see there's a lot of things that are not part of the range. In fact, again, I'll use the red. I can't get anything below 2, right? I can't get -1, I can't get 0, I can't get 1. None of the values below 2 seem to give me outputs. And also, I can't get anything that's larger than 10. Right? 10, anything bigger than 10 is out of my range. However, all of the numbers in here from 2 all the way up to 10 are in the range of this function, meaning that there is an input that would produce one of those outputs. So I would say that, again, there's two ways we can write this. One of them, I could say it's the y values from +2 to this case to I said 10 are possible outputs. And the other way I can write this with the other notation we talked about is I can say these are output values. So it would be y's. The smallest it could be would be a 2. And the largest it could be is 10. So my y's are everything between 2 and 10. The next question says, what is the value of f of 3, right? So you can see I'm giving this function an input, an x value of 3. So when I give this function 3, what does it give me? Well, I can see that on the graph that if I give this function the number 3, here it is. If I input 3, right, what does the function do? When I input 3, it's going to give me the number 10. So f of 3 is equal to 10. 3 goes in, 10 comes out. So I can write in this spot that I would write f of 3 is 10. When I give the function 3, it gives me 10. The next question says, what is the value of f of 6? So if I give the function 6, what does it give me? And if I come up here, I can say, well, I'm going to give this function the number 6. And if I give it the number 6, what does it give me? Well, it looks like it gives me over here. It looks like it goes all the way up and it gives me back the number 6. So if 6 goes in, 6 comes out. So f of 6 is equal to 6. And then the last question on this page says, what values of x will make f of x become 7? So this is kind of backwards from the problems that we just did. This time we're saying, look, I want to get an output of the number 7. I want this function to give me 7. I want it to give me the number 7. And if I look across here, those are all the y's that are 7, right? If I look at it, I says, well, what value of x is going to give me that 7? I can see there's two spots. One of them is right here, and the other one is right here. So apparently, if I give this function the number 2, it looks like it would give me an answer of 7. And if I give this function a value, an input value of 5, it would also give me an output of 7. So I would answer this question this way. I'd say, look, when you give f2 or when you give that function the number 5, right, 2 or 5 are going to produce an output of 7. Both of those will give me back the number 7. So our next page has a series of these expressions that we would like to simplify. Our final answer should avoid negative exponents. So for this first problem, if I look at it, I have factors of x and I have factors of y. Factors are those things that are multiplied together to produce a product. And I can see that I have 5 factors of x here, right? That's literally x, 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 x. There's 5 factors of x. And then I have 1 additional factor of x here. So in total, the things that are being multiplied, right, the number of factors of x I have is 6. So my answer is going to involve x to the 6th power because I have 6 factors of x. And then the other thing I have are factors of y. And you can see here that I have 3 factors of y and I have 7 factors of y. Well, if I have y, and I multiply that by y, there's 10 factors of y there, right? 10 y values are being multiplied together to produce a product. So I would say here that I have y, oops, wrong pen, y to the 10th power. So that's my answer for this. There are 6 factors of x, and there are 10 factors of y. My next problem, something is getting squared. In this problem, actually 2 things are getting squared. Within the parentheses, right, within the parentheses, that x is being squared, but not the 2. But outside of the parentheses, I can see I have 2 copies of everything that lives in the parentheses. Remember, my exponent tells me how many of those things I have. What do I have? I have 2x squared. How many of them? 2. So I can expand this as 2 times an x squared times 2 times an x squared. So you can see I've written that exactly twice. Now that I have that, and I'm looking at this, I'm saying, okay, now this squaring is not applied to this 2, right? This is just x squared. So inside of here, I've got a factor of 2, and then times xx, times another factor of 2, and then times xx. So what I'm looking at is 2 times 2, right? There's just 2 factors of 2. 1, 2 factors of 2. But then I have 4 factors of x, right? xx. So this is x to the 4th. So probably where I would leave this answer would be, I've got the number 4, which is the 2 times 2. And then I have 4 factors of x. So I would write this as 4 times x to the 4th power. And the next problem, we've practiced this a bit, rewriting this so that it's very evident what the giant 1 is, so I can think about and eliminate number 1s because they don't change a product. If I was to rewrite this numerator, I would say, look, I'm going to take this number 10, and I'm going to write it as 2 times 5. That's very clear to me that that is the same thing as 10, so I'm not changing this at all. I'm just changing how it looks. And in my denominator, I had a factor of 5. Okay, that's nice, because I can see now I've got a 5 factor in the top, 5 factor in the bottom, so that creates a giant 1. The other thing that I have is x to the 12th and x to the 7th. So I'm going to break up x to the 12th. I'm going to write it as x to the 7th, and then 7, 8, 9, 10, 11, 12, times an x to the 5th. So when I look at that numerator, I can see x to the 7th times x to the 5th is the same as x to the 12th. Now you may be asking yourself, well, why did you choose 7 and 5? I did that because I can see that I have 7 factors of x in my denominator. And by doing this, it makes it really clear that x to the 7th over x to the 7th is a giant 1. So what I have here is another 1 that I can get rid of. So my 2 1s are x to the 7th over x to the 7th and 5 times 5. So because those each equal 1, they're not affecting this product at all. So that means instead of including that in my calculations, right, the simplest form is I just have in the numerator a 2x to the 5th, and in the denominator, what is this, right? It's just the giant 1s. So it's 2x to the 5th over 1, and probably the preferred way to write that is just 2 times whatever x to the 5th power is. So this is the simplified expression that is equivalent to our original expression, right? You can see, and I identify that by just finding the giant 1s and eliminating, because again, multiplying by 1 doesn't change a product. For the next one, it's part D. Let's see, I've just got the number 5. That 5 is not being squared. The only thing that's being squared there is x. If I put parentheses, now it is 5x, but that's not what I have. I just have this. So I'm just going to write that single factor of 5 in the top, and then I'll write the x squared. In the bottom, I'm going to rearrange it. Instead of just x to the 5th, I'm going to go with an x squared times x to the 3rd. And again, I picked that because it very clearly identifies this giant 1, right? So now what I have is this 1 value of x squared over x squared, which is gone. X squared over x squared, which is gone. And in my numerator, I have the number 5. And in my denominator, I have x to the 3rd power. And that's exactly where we'll leave this. So do be careful. Pay attention once you identify the giant one and you get rid of it, where the pieces are, right? The 5 is clearly in the numerator, and the x cubed is clearly in the denominator. So I've got 5 over x cubed. All right, our next problem. Oh, how fun. This will be fun. So let's do the same thing, right? Let's try and break this up. So when I look at the a's in the top and bottom, I'm going to take this a to the fourth and I'm going to rewrite that as a squared, that's AA, times another a squared, which is AA. That's a to the fourth. And the reason why I broke it up that way is because you can see there's an a squared in the denominator. So I've taken care of my a's. Now let's take care of the b's. Well, in the denominator, there is this b cubed. And in my numerator, I'm going to rewrite b to the fifth as b cubed times b squared. So at this point, right, I can very clearly see I have a value of 1 in a squared over a squared. And I also have a value of 1 in terms of b cubed over b cubed. So that equals 1. So my final answer for this problem then would be in the numerator, I have an a squared. In the denominator, there is a b squared. I mean, in the numerator, there's also a b squared. They're both in the top. They're both in the numerator. They're above. My denominator has nothing but the number 1, right? What is it? It's a giant 1 times a giant 1, which equals 1. And I don't need to write a denominator of 1, right? That's not necessary. So my answer would be just square A, square B, multiply them together, and that's the answer. So instead of doing a to the fourth times b to the fifth over a squared times b to the third, if you just go a squared times b squared, you're going to get the same product every time, right? These are equivalent to each other. All of the values that this will produce for a and b match this one, right? And that's the joy of it, is that clearly we've simplified this. This is an easier expression for us to deal with. All right, and I think this is the last one, right? So on this last one, as I look closely here, I can see that I have 1, 2, 3 factors, 4 factors of a, and I have 1, 2 factors of b. So I've got a b squared. And I also have this single value of 3. So my answer is going to look like I've got a single factor of 3, and then I have a, and there's 4 of them, so I'm going to write that as a to the fourth power. That's AA. And then I'm going to have b, and I'm going to square that. That's b times b. So this is my answer, 3a to the fourth, b squared. Is our answer for F. All right, let's move on to our third page. For our third page, there are 2 parts, question 4 and question 5. And for 4, we're asked to solve 4 linear equations. And I think my advice to you as you're doing these is don't necessarily write the steps of what you're doing. Just write what it becomes, and then just verify that that's really what's happened. So when I look at this, what I say to myself is, I'm going to add 7 to both sides of this, right? That's an allowed thing, right? It's an allowed property of equality. If you have equal things and you add equal things, you get equal things. So if I add 7 to both sides, on the left-hand side, it's just going to become 12x, because -7 plus of 7 is going to make a 0 there. And on the other side, I've got 17, and when I add a 7 to that, it's going to give me the value 24. So what did I just do? I added 7 to each side. I added 7 to the left. I added 7 to the right. I know that these 2 equations are equivalent because of the addition property of equality. The next thing I'm going to do is I'm going to divide both sides by 12. And I know that if I have equal things and I divide both sides of that by things that are not 0 but equal things, as long as they're not 0, I get equal things. So 12 times x divided by 12 gives me just plain old x. Oops, I don't need that pen. It gives me just plain old x. 12x divided by 12 is x, and 24 divided by 12, and if you're not sure, check that with a calculator. 24 divided by 12 is the number 2. So again, what did I do? I divided both sides by 12 in this case. Now, how do I know that my answer is correct? Good question, fair question. One of the things that you can do is just grab a calculator and say, look, I'm going to take the number 12 and I'm going to multiply it by what I think x is. I think x is 2. And then I'm going to subtract 7. I know that this is correct if I get the number 17, because the solution is going to make it it's going to make it so that this statement right here is legit true, right? That both the left-hand side and the right-hand side are the same. And yeah, you can see when I press enter on my calculator, 12 times 2 minus 7 is 17. So it made both the left-hand side and the right-hand side was already 17, so I know that that's my solution. Next equation. Here we go. So for this one, I'm going to start by taking away a 1 from each side. So I'm going to subtract 1 from each side. So on this side, I've got 4x. There was a plus 1, but because I'm subtracting 1, it's gone. And on the other side, I have an x. I also have this negative 5, and I'm going to subtract another 1 from that. So negative 5 minus 1 more is going to give me negative 6. So what did I do to both sides there? I subtracted the number 1. Now what am I going to do next to both sides? I'm going to take away an x from each side. On the left-hand side, I've got 4 x's. If I take away 1x, that's going to give me 3, right? If you have 4 apples, take away an apple, you got 3 apples. On the right-hand side, there is an x, but I'm taking 1 away. So instead of having an x minus 6, it's just going to be negative 6 because I took away the x from both sides. And then finally, I'm going to divide both sides by 3. So 3x divided by 3 is x. And on the other side, negative 6 divided by 3 is the same thing as negative 2. So negative 2 is my solution here. If I take that number and I plug it into my calculator, right, it should give me that both sides are going to be exactly the same. So I'm going to clear this, and I'm going to go 4 times, and I'm very careful here. This is how I get a negative number. So I hit this negative and then 2. So that's 4 times negative 2 plus 1. Okay. And on the other side, I'm just going to go a negative 2 and then minus a 5. And you can see that when I enter negative 2 onto both sides, right? I do what it says for the left, and I do what it says for the right. When I do that on both sides, I get both sides become negative 7. So x equals negative 2 is indeed a solution. It makes the left-hand side and the right-hand side the same. For C, I'm going to choose to use the simplest form of this thing we call the distributive property. So I'm going to go ahead and rewrite the left-hand side as 8x. Let's see, because I can distribute this multiplication problem across these two terms. So this is equivalent to 8x plus the number 4. And if you're curious why is that true, ask me in class and I'll give you a mini proof on why this is the case. And then on the other side, I'm just going to rewrite 20. So the question is, did I do something to both sides? No, I didn't do something to both sides. What I did is I rewrote the left-hand side with something that's equivalent to the left-hand side. So what I have here now is equivalent to what I had before. Now what I'm doing is, well, I'll write it. You can look at that and say, what did he do to both sides? I took away 4. Right? Each side I subtracted 4. What am I doing to both sides? Divided both sides by 8. 8 times x divided by 8 is x, and 16 divided by 8 is 2. Divided both sides by 8. So I believe that my answer is the number 2. If I plug that into the equation, right? If I come in here and I plug that in, oops, let me clear the equation, or clear the calculator and go to the calculator. Sorry. I'm just going to go 4 open parentheses 2 times 2 plus 1 close parens, and you can see, yeah, it's 20. So when x is 2, it forces the left-hand side to become 20, which is what the right-hand side is. Right, there's one final problem here, and I think I'm definitely going to go ahead and use the distributive property, again for this one. So let's see. I'm going to rewrite the right-hand side. So instead of this being what it is, I'm going to write 4x and then minus the number 40. So you can see what I've done as I've distributed this 4 to both the x and the negative 10. So it's now 4x minus 40. Over on the other side, I've got 12 plus 2x. So let's see. Next, I'm going to add 40 to each side. So if I add 40 over to the right-hand side, that's easy. That's just going to become 4x. So I've got a negative 40 and I added 40. And when I add 40 to the left-hand side, that's going to become 52 plus 2x. So what did I do in that step? I added 40. Now I'm going to take away 2x from each side. If I take away 2x from the left-hand side, it gives me 52. And when I take away 2x from the right, it gives me 2x. And then finally, I'm just dividing both sides by 2. 52 divided by 2 is 26. And over here, 2x divided by 2 is what x is. So x is the number 26. So I know what x is. And I'm just going to quickly verify that it really is a solution. Let's go to bring up our calculator here. So on our calculator, you can see I'm plugging in 26. One thing you can do with these calculators, you can take this number 26 and just press enter. So it's on the stack, I'll call it. And I'm just going to go 12 plus 2 times. Oops. I'll go up, grab the 26, and I press enter, and boom. And you can see it made it 64. On the other side, I've got 4 times, open parentheses, go get the 26, there it is, grabbed it, minus the number 10, close parentheses, and boom, when I press enter, you can see it made it 64. So when I enter 26 into both sides of this equation, it turns both sides into 64. So yes, 26 is a solution because it makes both the left and the right equal the number 64. So we're going to pick this up with part 2, and I'll be starting with question 5 when we come back. Okay, so on page 3, we also have question 5, and it asks us to evaluate the following 2 functions for different input values. So one of the functions is f of x, and the other one is g of x. And I just as a model, I'm just going to come down here and I'm going to say, look, f of x is equal to 4 times whatever x is plus 1, right? I could do the same thing for the next problem below. F of x is always 4 times whatever x is plus the number 1. There's another one of those over here, right? I'm just copying down this rule, right? It says what the rule is for f of x. So over here, I'm going to write f of x is 4 times whatever x is plus 1. Now, you notice I'm not writing down the x. What I'm doing is I'm writing in instead a place to place an x, right? So in this case, when they tell me x is the number 3, I'm going to place a number 3 right in there, right? That didn't work. I'm going to place a 3 in there. Oh, so f of 3 is 4 times 3 plus 1, right? 4 times 3 is 12. Plus 1 is 13. So when the function f gets 3, it gives me 13, right? I give it 3, it gives me 13. F of 3 is 13. The one below that, if I give the same function 0, what's it give me? Well, if I give it 0, boop, I just gave it 0. I put 0 into it. And 4 times 0 is 0 plus 1 is 1, right? 0 plus 1 is 1. So when I give this function f 0, it gives me back the number 1. The other one over here was f of 4, right? When I give the function 4, right? When 4 goes into it, plop, there it is. There's a 4 that got placed in that function. It gives me back 4 times 4 is 16 plus 1 is 17. So I could say f of 4 is 17. You give it 4, it gives you 17. Okay, so those were all f. Oh, there's another one, f of 10. We're here, let's do this. So again, it's the same definition. F, the function f right now is defined as 4 times whatever x is plus 1. So you're going to give it this x, and then it's going to tell you what it becomes. So 10 goes into the function, doop, there it is, right? 10 got placed into it. When I put 10 into that function, it gives me back 4 times 10 plus 1. It gives me back 41. All right, so we can see on the function f what happens when I give it 10, when I give it 4, when I give it 0, and when I give it 3. Now there is another function, g. And the definition of g is different. G says the following. It says, look, you are going to place x into the function g, subtract 4 from that, and once you get that answer, you're going to square the result. What? It says that. It says, right, g of x is, parentheses, x minus 4, and then square that result. So why am I putting these extra parentheses here? It's really good practice, right? When I'm identifying the location where I have to sub in my variable, to just put extra parentheses there. Especially if the number is positive or negative, it helps. So if I look at this function says, well, what, get out of here. This function says, when you give it 2, what does it give you back? Well, let's answer that question. I'm going to give it 2. Okay, so what do I have in these parentheses? Well, I've got 2 minus 4. Okay, I've got 2 minus 4, which is negative 2. And I'm going to square that. To square something means I'm multiplying it by itself, right? So I've got a negative 2 factor times another negative 2 factor. Negative 2 times negative 2 is positive 4. So when I give G 2, I get back a positive 4. All right, the last question here is complicated a little because it uses both G and it uses F. So I remember that the function F was what? F was 4 times whatever the input is plus 1, right? So this 2 is going to go into that. And then I'm adding to that whatever G of 0 is. And G was what? It's like, G was like, you're going to put in X, and then you're going to subtract. Ooh, does it subtract 4? I got to go see. I forgot. I got to go peek. Yeah, then you subtract 4, and then you square the result. So, and then I subtract 4, and I'm going to square that. So I'm going to place 0 into the function G, and I'm going to place 2 into the function F. Okay. When I plug 0 into G, this becomes what? It becomes negative 4 gets squared. Negative 4 times negative 4 is 16. And 2 that I'm going to add, 4 times 2, which is 8, plus 1, I'm going to add 9. So 16 plus 9 is what I get when I add G of 0 and F of 2. 16 plus 9 is, it's been a long day. It's 25, isn't it? Yeah, it's 25. 25, because I'll take the 4 from the 9, and it's 25. So this right here is the number 25. G of 0 plus F of 2 is 25 when G and F are defined like this, right? So I'm using the definitions that were given in this problem to find these. All right, let's move on to our final page for our test. We're going to go on to page number 4. So for question 4, we're asked to create a table, a graph, and an equation to match the tile pattern below. We're also asked to sketch figure 0 based on the pattern we see, and to use one of these representations. It doesn't matter if it's the pattern or the graph or the table or the equation to figure out how many tiles will be in the 8th figure in this sequence. So one of the things I like to do is kind of see how things are growing here. And if I grab this little red pen, I can say, well, look, every single time that I move forward, it looks like I'm just adding a tile at each of the sides, right? It's growing by 1, 2, 3, 4. So my growth is by 4 every single time. And to figure out what the 0 figure is, I'm just going to go backwards. I take away 4, I'm here. Take away 4, I'm here. And if I take away those 4 red tiles, what I'm left with is just this one square tile right here, right? So this is where I begin. That's not a square. This is not a square either. It's terrible. I can ask it to try and make a square. Is that better? No, it's not. How about this? Okay, close enough. So I start with this one square here. So I can see a couple things, right? If I want to take this situation of these tiles and translate it to this table of values, I can see, oh, at figure 0, I have just a single tile. By the time I jump to figure 1, you can see I now have 1, 2, 3, 4, and 1 in the middle. I have 5 tiles. And when I jump to figure 2, I have the 5 plus 6, 7, 8, 9. So I just added 4. And then the 9 plus 9, 10, 11, 12, 13. So I go to 13. And the 4th and the 5th. So each time, the number of tiles I have is just growing by 4 more. So 13 plus 4 would give me 17, 17, 18, 19, 20, 21. I'm up at 21 tiles. So there's a representation. I can also go ahead and take and look at this as a graph. It's a little tricky here, and I do see that this is the number 2. and this is the number 4. So that means in between 0 and 2 has to live number 1, and in between 2 and 4 has to live the number 3. So I'll make sure I recognize that. So at figure 0, I have a total of 1 tile. So I'll just put a 1 there. At figure 1, I'm up to 5 tiles. At figure 2, I jump to 9. Figure 3, we're landing all the way at 9, 10, 11, 12, 13 tiles. And at figure 4, I have to get to 17. That's 15, 16, somewhere up here, about up here. Now, I'm fortunate, right? I've got a beautiful electronic ruler that I can rotate, and I can line up with this. And I can grab a pen. I don't know what color pen. I'll just get this little yellow pen or green pen. Well, I didn't quite hit the things, but it's close, right? So this is another representation. Now, if I want to figure out the 8th pattern, I could extend this to 6, 7, 8, and I could use that, add 4, add 4, add 4 to figure out the 8th one. But I can also just use the equation, right? So if y is my number of tiles, and my growth is 4 tiles every time, right? There's my growth, 4x, plus the base where I begin with 1 tile. That equation represents this situation. And as a check, if I put the number 4 in there, I do get 16 plus 1, which is 17. If I put the number 2 in there, I do get 8 plus 1, which is 9. So I see it's behaving correctly, right? If I put in 5, 4 times 5 is 20 plus 1 is 21. So if I put in 8, right, 4 times, I want the 8th value in the sequence, I get 32, oops, I don't want that pen, 32 plus 1, no, I wrote 33, 32 plus 1 more is the 33. So that's it for the very last question on this this study team test, right? I just consider this kind of a basic look at some of the things that we've been talking about so far in chapter 1 and things that we might talk about in the future. I hope this was helpful, and I will see you in class hopefully tomorrow.